Hi from Tokyo, Japan, and welcome to Jeremy's IT Lab. This is the first video in the routing section of the course. We'll start with a few general topics before we get into the specifics of EIGRP, OSPF, and BGP, the three dynamic routing protocols covered on the exam. In this video, we'll start with static routing. Of course, static routing is something you should already be comfortable with from the CCNA, but it's worth doing a bit of review to make sure there aren't any gaps in your knowledge. Here's what we'll cover. We're going to focus on configuring the various types of static routes. There are host, network, and default routes, categorized based on their destination. Then there are recursive, directly connected, and fully specified routes, categorized based on their next hop. And we'll also review floating static routes. We'll cover how to configure all of these route types in both IPv4 and IPv6. Let's get started. Let's begin by reviewing host, network, and default routes. Routes can be categorized based on their destination prefix. This is true of any type of route, not just static routes. Prefix, by the way, means a network address and a prefix length, such as 192.168.1.0/24. That's a prefix, also called a network prefix, or just a network. The terms are generally interchangeable. So how can we categorize routes based on their destination prefix? For example, a host route is a route to a single destination IP address. It's a route to one host, hence the name host route. In IPv4, this is any route to a /32 destination prefix. A /32 route matches a single IPv4 address. And in IPv6, it's any route to a /128 destination prefix, matching a single IPv6 address. A network route, on the other hand, is a route to more than one destination IP address. Instead of just a single address, it's a network of addresses, like a /24 subnet. In IPv4, that means any route to a /31 or shorter destination prefix. Shorter meaning a shorter prefix length, /30, /24, /18, whatever. And in IPv6, it's any route to a /127 or shorter destination prefix. Usually, this means /64, but it doesn't have to be. And finally, a default route is a catch-all route that matches all possible destination IP addresses. In IPv4, it's a route to 0.0.0.0/0. And in IPv6, it's a route to /0. Although a default route with a /0 prefix length fits the above definition of a network route, default routes are generally not considered network routes. This is because instead of being routes to a particular destination network, they are simply catch-all routes that are used for packets that don't match a more specific host or network route. For this video, we're going to use this simple network. It's using dual stack IPv4 and IPv6, meaning it's using both at the same time. There's not much to explain, but I want to point out R1 and R3's loopback 0 interfaces. In labs, it's common to use loopback interfaces to represent LANs like this, because they're quick and simple to set up. Later, we'll configure static routes to provide connectivity between the two loopback networks. But for now, let's see what routes already exist. Here's R1's routing table. It has two connected networks, 192.168.1.0/24 and 12.0/30. As you already know, a router adds two routes to its routing table for each IP address, a connected route to the connected network, and a local route to the specific IP address of the interface. These two connected routes are network routes. R1 has a route to the 1.0/24 and 12.0/30 networks. The two local routes are host routes, routes to R1's IP addresses, 1.1/32 and 12.1/32. And here is R1's IPv6 routing table. It has two connected routes, which are network routes to /64 subnets. It also has two local routes, which are /128 host routes, to the addresses of its interfaces. There's also a route to FF00:8, the IPv6 multicast range. We'll cover multicast routing in a later section, so don't worry about it for now. The next hop of this route is the null zero interface, another topic we'll cover soon when we look at route summarization. So those are the three types of routes based on destination: host routes to a single IP address, network routes to a network of addresses, and default routes, catch-all routes that match all possible IP addresses. Without configuring any static routes, these routers already have multiple host and network routes in their routing tables, thanks to the connected and local routes they automatically added. So, routes can be categorized based on their destination, but they can also be categorized based on their next hop. There are 3 kinds. Recursive routes specify only the next hop IP address. Directly connected routes, also called directly attached routes, specify only the exit interface, the interface that will transmit the packets. And fully specified routes specify both the next hop IP address and exit interface. Let's start by looking at recursive routes, configuring them on R1. First, I configured a recursive IPv4 static route to 192.168.3.0/24 with 12.2 as the next hop. And here's R1's routing table after. Notice the route only has next hop IP address information, not the exit interface. And here's the IPv6 equivalent. First, I used IPv6 unicast routing to enable routing of IPv6 packets. This is an easy command to miss, since IPv4 doesn't need it, but always make sure to enable it on your routers using IPv6. Let's clarify what this command actually does. Without the IPv6 unicast routing command, the router can have IPv6 addresses and can send and receive IPv6 traffic like a host, but it will not route IPv6 packets. In other words, it won't pass IPv6 traffic from one interface to another. It functions like an IPv6 host, not an IPv6 router. So you need this command to allow the router to actually route IPv6 packets. Anyway, here's the route I configured to R3's loopback 0 network, specifying only the next hop IP address. And here's the routing table. This route and the IPv4 one are both network routes, since their destinations are networks rather than individual hosts. But they are also recursive routes, since they specify only the next hop IP address. Now, why are these routes called recursive? It's because they require multiple routing table lookups to resolve the next hop and forward the packet. First, the router does a lookup to identify the next hop IP address. But with that information, it still doesn't know which interface to send the packet out of. So it then performs a second lookup to find out how to reach the next hop IP address. For example, if R1 wants to forward a packet for 192.168.3.1, it will look up the address in its routing table and find that it matches the static route to 3.0/24. It learns that the next hop is 192.168.12.2. So it then performs a second lookup for 12.2 and finds that it matches the connected route for 12.0/30, which is connected to the G1 interface. Now it can use ARP to learn the next hop MAC address and then forward the packet. The process is the same for IPv6. The destination is 2001 DB83:1, so it performs a lookup for that address and finds that it matches the static route. Then it performs a second lookup to find which interface the next hop IP is connected to, before it can actually forward the packet. This may sound inefficient, but it really isn't a big deal. After the first packet, Ceph, Cisco Express Forwarding, caches the result in the FIB and adjacency table, so subsequent packets are hardware switched without any more routing table lookups. The router only does the recursive lookup once. Next, let's look at directly connected routes, specifically for IPv4 first. Directly connected routes specify only the exit interface. In other words, the outbound interface that will transmit the packets. They have this name because the route's destination prefix appears as a directly connected route in the routing table, and the router will behave as if it is directly connected. These routes rely on proxy ARP to function. We covered proxy ARP and directly connected routes in the ARP video of the course, so review that video if you don't remember. But now, let's see why directly connected static routes are usually not a good idea. On R2, I configured directly connected routes to R1's and R3's LANs, specifying only the exit interface. Here are those routes in the routing table. R2 now thinks that 1.0/24 and 3.0/24 are directly connected to its interfaces. To test, I pinged 192.168.3.1, which is the IP address of R3's loopback 0 interface. I also pinged a few other IP addresses in the subnet, which I'm not showing here. And here is R2's ARP table after those pings. I pinged 192.168.3.1, 2, 3, 4, and 5, as well as R3's G1 interface at 23.2. Notice that they all share the same MAC address. That's the address of R3's G1 interface. Proxy ARP is enabled on R3G1, so it replied on behalf of the IPs in the 3.0/24 subnet. Looking at R2's ARP table, you can see a big problem with directly connected static routes. Every host in the route's destination prefix is treated as directly reachable, so the router ARPs for every single one. Instead of just using ARP to learn the next hop MAC address, R2 ARPs for each IP address in the 3.0/24 subnet. This can overwhelm the ARP table and CPU. In a small network like this, it's not an issue at all. But imagine a directly connected default route to the internet. The router would think that every single host on the internet is directly connected, and that definitely has the potential to cause problems. The router would create an ARP table entry for every destination on the internet. Directly connected routes work fine on serial links, which don't use MAC addresses and ARP. Serial links are exclusively point-to-point in nature, so they don't require MAC addresses to indicate each frame's destination. A frame sent out of a serial interface must be destined for the device at the other end of the link. But you really should avoid this kind of route on Ethernet links. And in modern networks, serial links are largely a thing of the past. Ethernet is king when it comes to wired connections. And now let's look at directly connected IPv6 routes. On R2, I configured routes to R1 and R3's LANs, specifying only the exit interfaces. Here are those routes in R2's routing table. Everything looks good, so let's see if R2 can ping R3's loopback interface. Unfortunately not. The ping failed. R2 has a route to loopback 0 subnet, 2001 db83:/64, but it can't ping that subnet. IPv6 directly connected static routes can be configured and will appear in the routing table, but they won't work on Ethernet links. And why is that? Well, directly connected IPv4 routes rely on proxy ARP, but there is no equivalent proxy NDP in Cisco iOS. So R3G1 can't respond on behalf of loopback 0. When R2 sends a neighbor solicitation message to learn the MAC address, the message is destined for a different IP address, so G1 simply ignores it. IPv6 directly connected static routes do work on serial links, which don't use MAC addresses, and thus don't need to exchange neighbor solicitation and advertisement messages. But on Ethernet links, they don't work. So in general, in both IPv4 and IPv6, you really shouldn't be using directly connected static routes in modern networks that only use Ethernet. Recursive routes are a much better option, as are fully specified routes, which we'll cover next. But first, let's change these routes from directly connected to recursive, so the pings will actually work when we ping between R1 and R3's loopback interfaces later. Now let's look at the last of these three route types. Fully specified routes specify both the next hop IP address and the exit interface. Because they specify both, they are more efficient than recursive routes. They only require a single routing table lookup instead of two. But as I said before, in practice there is very little difference thanks to Ceph. After the first packet to a particular destination network is forwarded, an appropriate Ceph entry is made, and further packets won't need recursive lookups. Now let's configure some fully specified routes on R3. First, an IPv4 route to R1's loopback 0 network. I specify both the exit interface, G1, and the next hop IP, 192.168.23.1, which is R2G2's IP. And here's the route in the routing table. So, now we should have IPv4 reachability between R1 and R3's loopback interfaces. But before we test, here's the equivalent IPv6 route to R1's loopback 0. And here it is in the routing table. Now let's test some pings between R1 and R3. From R1, I ping 192.168.3.1, R3's loopback 0, but the ping fails. And same for the IPv6 ping. Any idea what's causing this? We have all of the routes we need between the two loopback networks, so the issue is something else. Here it is. By default, a ping source IP is the address of the interface that sends the packet. So, R1 sends the IPv4 ping from 192.168.12.1, its G1 interface. But R3 doesn't have a route to reach 12.1, so it can't reply. And the same thing for the IPv6 ping. We configured reachability between the two loopback networks, but not the transit links between the routers. Of course, to fix this, we could configure additional static routes on R1 and R3. R1 needs a route to 192.168.23.0/30 between R2 and R3. And R3 needs a route to 12.0/30 between R1 and R2. But let's try a different solution. You can specify a ping source IP with ping, followed by the destination IP, then source, and then either the interface or specific source IP. If you specify an interface, it will use that interface's IP. If you specify an IP, it will use that IP, of course. But it has to be an IP address that is actually configured on the router. You can't just choose a random IP address. The command will be rejected. So here's the IPv4 ping. I specified source L0, so R1 sends the pings with a source IP of 192.168.1.1. This time the ping works. Same for the IPv6 ping. I specified source L0, and this time it works. With a dynamic routing protocol like OSPF, R1 and R3 would automatically learn about the transit links connecting each other to R2. But with static routing, that doesn't happen. You can either manually configure the routes, or you can specify the ping source like this. The final topic we'll touch on is floating static routes. There will be a separate video about route selection, and in that video we'll also cover this topic. But since this video is about static routing, let's briefly touch on floating static routes by reviewing what you learned in the CCNA. Floating static routes are configured with a higher administrative distance to make them less preferable than another route. Static routes have a default AD of 1, but to configure a floating static route, simply add the desired AD value to the end of the command. For example, in the network below, let's configure routes on R1 to reach R5's loopback 0, the 192.168.5.0/24 network, and the 2001 DB85:/64 network. Here's how I configured the IPv4 routes. Before I show the routing table, what do you think is the effect of these commands? Which route or routes are active and which are backup? Well, two of the routes have the default AD of 1, and the third route, via R4, has an AD of 2. Notice that in the second route, I specified an AD of 1 at the end. That's the same as the default AD, so it won't actually have any effect. I just did that to demonstrate. So R1 inserts the routes via R2 and R3 into its routing table, while the route via R4, a floating static route, will only enter the routing table if both of these routes are lost. And here are the IPv6 routes. Just like in IPv4, to configure a floating static route, just add the AD to the end of the command. Once again, I configured the route via R4 as a floating static route with an AD of 2, one higher than the default of 1. So just like in IPv4, the routes via R2 and R3 enter the routing table, while the route via R4 is waiting as a backup. Alright, that's basically what you learned about floating static routes in the CCNA. We'll cover a few more details in the route selection video, but that's all for now. Before we do a short quiz, let's review what we covered. I hope you already learned these concepts in your CCNA studies, but in any case, it's worth reviewing before we move on to more complex topics in this section. So we started by categorizing routes based on their destination prefix. A host route is a route to a single destination IP address. In IPv4, That means any route to a /32 destination prefix, and in IPv6, it's /128. These are routes to a single host, so they're called host routes. A network route is a route to multiple destination IP addresses. In IPv4, that means a /31 or shorter prefix length, and in IPv6, it's /127 or shorter. These are routes not to a single IP address, but to a network of addresses. Finally, a default route is a catch-all that matches all possible destination IP addresses. In IPv4, it's a route to 0.0.0.0/0, and in IPv6, it's to :/0. Default routes are most commonly used for internet connections. Alright, those are the 3 ways to categorize routes based on their destination type. You can also categorize routes based on their next hop. Recursive routes specify only the next hop IP address. Here's how to configure them in IPv4 and IPv6. The second type is directly connected routes, also called directly attached routes, which specify only the exit interface. In IPv4, these routes only work if the neighboring router has proxy ARP enabled. But IPv6 directly connected static routes don't work on Ethernet links at all. There is no proxy NDP in Cisco iOS. And these routes should be avoided in IPv4 too, since they needlessly expand the router's ARP table. Finally, fully specified routes specify both the next hop IP address and exit interface. These are the most efficient, but in practice you won't notice any difference between them and recursive routes. Okay, at last we covered floating static routes, which are backup routes configured with a higher AD than the primary. Configuration is simple. Just add the desired AD value to the end of the command. We'll see floating static routes in action in later videos. Alright, that's what we covered in this video. Now let's do a short quiz to test your understanding. Here's quiz question 1. Which of the following commands configure a recursive host route? Select 2. Pause the video now to think about your answers. Okay, the correct answers are A and B. A is an IPv4 route to a /32 destination prefix, making it a host route. And it specifies only the next hop IP address, so it's recursive. And B is an IPv6 route to a /128 destination prefix, specifying only the next hop IP address. C is a host route, but it's fully specified. Same for D. E and F are both recursive, but they're network routes, not host routes. Okay, let's go to the next question. Which of the following commands configure a fully specified floating network route? Select 2. Pause the video now to think about your answers. Okay, the answers are C and F. C is an IPv4 route with a /24 prefix length, making it a network route. It specifies both the exit interface and next hop IP, so it's fully specified. And it has an AD value higher than the default of 1, so it's a floating static route. F checks all the same boxes, but it's an IPv6 route. A is a floating network route, but it's recursive, not fully specified. B is a fully specified network route, but it's not floating. It specifies an AD, but it's the default value of 1, so it's the same as not specifying an AD at all. D is fully specified and is a floating route, but it's a host route, not a network route. And E is like B. It's a fully specified network route, but it's not actually floating because its AD is the default of 1. Okay, that's all for the quiz. And that's all for this video on static routing. We mostly just reviewed topics from the CCNA, but it's important that you really have these basics down before we cover more advanced routing topics. Coming up next, we have videos on dynamic routing, summarization, VRF, policy-based routing, and more. And then we'll finally dive into EIGRP, OSPF, and BGP. I hope this video was helpful. Thanks for watching. Before we wrap up, I want to say a quick thank you to the channel members whose names you see on screen. Your monthly support helps me keep making these videos and keep this content free for everyone on YouTube. I really appreciate it. Thank you for your support. If the video was helpful and you want to support me, click the join button under the video. Thanks again.